All right, so one of the things that you guys have again expressed that you're struggling with is this whole transition from either rotating, so rotating, and into rolling with slipping. I'm sorry, not into rolling with slipping, but into rolling motion. And so there's going to be some period of time where some slipping takes place. And the other case being when something is skidding. So this is the case where something is skidding. I guess case 2 I could label as skidding, but that this object eventually begins to roll. Okay, so case 1 is slipping, and the other one's skidding. They're both kind of termed rolling with slipping. They fall under that same kind of heading, but at the same time, they're really two different things. In our first situation, in what I'm calling case 1 in slipping, I have something that's spinning really fast. Think of being at a stop sign on a wet day, and you hit the gas pedal too hard, and so you start to spin your tires. Well, that's because this thing is rotating too quickly for its translational speed. We're going to talk more about that in a second. The second situation is kind of like when you play pool. If you hit something so that it starts traveling, the center of mass starts traveling at a certain speed, but it's rubbing against a surface down below, well, eventually this thing stops skidding and ends up rolling. And so there's a transition between these two, between this phase, which is skidding, and where it actually starts to roll. So we want to talk about what's going on with these conceptually in both cases. I've already made videos showing you how to do the algebra from there, so you're just going to have to go back and watch those videos again. And if you're still stuck, I guess then come see me. But part of this responsibility falls back on you. But I'll at least go through the concept of what's going on this. Okay, so rotating this way at omega equals omega 0 is what I've got going on in this slipping case. What I'm going to do with this thing, this wheel that's just spinning right now around its center of mass, is I'm going to take it, I'm going to put it in contact with the ground. So we want to draw a free body diagram of what this looks like when it comes in contact with the ground. Okay, so I'll attempt to draw a wheel. I'm just thinking of a hollow hoop. It doesn't matter if it's solid, hollow, whatever, in terms of what we're talking about today. Pretend that's a wheel. I might even have to label that. It's drawn so poorly, but whatever. Okay, so as this thing comes in contact with the ground, what forces are acting on it? Well, you still always, I don't want a line that big. You still always have gravity. Okay. You would have some normal force coming up from the ground. And then you'd have to ask yourself, well, there's friction. This thing is rubbing against the ground. What direction is that friction acting? Okay, so it's spinning this way. So right now, this surface is trying to slide past the ground going this way. Well, we know friction always opposes the attempt to slide past each other. So friction is going to be acting at the base of this wheel, and it's going to act that way. Okay, so now ask yourself, as time passes, what's going to happen to the velocity of the center of mass, and what's going to happen to omega? Okay, and there's two pieces with this that we can really use to understand it. If I look at what happens to omega, well, omega is related to the rotational motion of this thing. So that's all about torque. Okay, so I can say that looking at the net torque around the center of mass of this wheel, that's equal to I times alpha. And again, I said it doesn't matter if it's a hollow wheel or a solid wheel. I'm just going to say it's I for now. All right, well, what things are exerting a torque around this center of mass? Well, gravity's not. Gravity acts right at that radius. There's no distance. Normal force isn't. It acts right through the radius. But friction acts perpendicular to a radius from there. Well, friction's exerting a torque then. So you could say that the force of friction times whatever the radius of this rod, hoop, wheel thing is, I'll give that a capital R, is equal to I times alpha. Okay, is that friction going to make it speed up or slow down? Well, friction is acting against this attempt at sliding, so I think that omega, as time passes, is going to decrease. Okay, this alpha is going to be a negative number. It's going to make this thing slow down. What about the net force side? Well, net force we know is equal to mass times acceleration. Vertically, there's no net force. Gravity acting down, normal force acting up. If I was really good at drawing my pictures, I should have drawn these two vectors equal in size. I was a little lazy and a little sloppy. I'm not going to fix it. Okay, horizontally, I have an unbalanced force of friction. So my net force is the force of friction. That's equal to the mass of this thing times its acceleration. All right, well, that acceleration is going to then depend purely on this friction. We could plug in like a mu and a normal force, say that's equal to ma. We could say that that normal force in this picture is going to be mg. And so basically we can see that this thing is going to have some kind of linear acceleration. It's going to gain speed as time passes because the direction of the force and the direction we expect this thing, we have an unbalanced force, let's put it that way. We have an unbalanced force in this direction, so that's going to make the velocity of the center of mass increase as time passes. Okay, when does this thing start to roll without slipping? Well, we know that the rolling without slipping condition is when the velocity of the center of mass equals r omega. So when this happens, the thing starts to roll without slipping. So things you'd be asked for. You might be asked how much distance does it travel before this thing rolls without slipping. You might be asked how much time does it take for this thing to roll without slipping. Well, in both of these situations, this force of friction is a constant, so this alpha is a constant. So you can write a gang of 5 rotational equation, a kinematics equation for rotation, like omega final equals omega original plus alpha times time, that will relate this acceleration and this time and deal with that side of it. On the linear side, looking at this, the only force acting is friction. Again, it's constant in size. So you could write a kinematics equation like Vf equals Vo plus At, where you know this acceleration. And then this thing will roll without slipping when this condition is met. And so you can solve for or find a way to relate these V's and these omegas. And that's what we did, and I have other videos and other sample problems on that, so I'm not going through that again. Okay, that's the concept for case 1. For case 2, it's a similar idea, just kind of reversed. Now this object has a whole lot of translational speed, but it's not spinning yet. But it's going to end up rolling without slipping, so it's going to end up having that condition that the velocity of the center of mass is equal to r times omega. All right, well right now, this is some original value, V original, and this is 0. Well, what has to happen for these two things then to make this take place? Well, it seems to just kind of, maybe shortening the discussion here a little bit, it seems like as time passes, this has to get bigger, because right now you can't have something equals something times 0 and have these two be equal unless they're both 0. And it seems like then that would probably get smaller. Okay, a free body diagram would probably help us out with that. So let's draw a free body diagram to help us. That was a much better wheel. Okay, what forces are acting on this? Well, we have gravity. We have normal force acting from right there at the base. And then, again, this wheel is skidding across the ground. So as this wheel is sliding this way, because the velocity of the center of mass right now is directed that way, what direction is friction acting? And hopefully you're saying, well, friction is opposing that motion, so the force of friction is going to act this way. Okay, well, when this force opposes that velocity, it's going to decrease this velocity. So as time passes, the velocity of the center of mass goes down. Okay, at the same time, and I can do that with net force equals ma. Let's do that really fast. So net force equals mass times acceleration. My force of friction is opposite my velocity, but that force of friction is what's responsible for causing my horizontal acceleration, because vertically those two forces are balanced. Okay. On the rotational motion side, I can look at this and say torque net around the center of mass is equal to I times alpha. What forces are exerting torques? Not normal force, it acts straight through the, or sorry, it acts normal force acts parallel to the radius. Not gravity, there is no radius, and it acts parallel to the radius, but friction acts at a right angle to the radius. So I get a torque of force of friction times that radius equals I times alpha. This is constant, which is going to give us a constant alpha. This is constant, which is going to give us a constant A. I can write a rotational motion equation for this. Okay, that red didn't show up so well. Let me just erase part of my circle. I can do it with the velocity side. Again, I can use kinematics equations, gang of 5 equations, because those accelerations are constant. Time is in both of these. I know that this thing rolls without slipping when this condition is met. You do some algebra from there. Or if they were asking for distances, I'd want to write this in terms of distances, so like omega final squared equals omega original squared plus 2 alpha times change in theta. And on this side, I'd write it as, I guess I could do it as arc length or distance or anything like that, or I could do it with velocity. The algebra part I'm not as worried about. Or if I am, well, if you're struggling with that part, well, then you just need to crank through it until you can figure it out. And again, I've got lots of examples posted that will do that. But this is a concept behind the two cases for transitioning from slipping to rolling without slipping, or from skidding to rolling without slipping. Okay? So that's what's going on.